In this video, we will predict the motions of a moving tennis ball of 0.06 meter diameter and 0.05 kilogram of mass. For setting, the object is placed on the positive x directions of our Cartesian plane, be moving from right to left of the negative x direction. Displacement time is 3 seconds. So we will use 2 points from the displacement of the object to calculate the velocity by computing in the equation these two values of the tracker. After carrying out the calculation, we end up with velocity equal to x component negative 0.424 and y and z component equal to 0. Keep note, our observation time is 0 seconds and the time of observations is 0.867. Our next step is applying this information into a computer model. By using Python, we will directly input first the ball mass in kilograms, 0.05, specify the ball position in vector form, 0.0410, 0, 0, the ball velocity in vector form, negative 0.424, 0, 0, time started, which is 0 seconds. Importantly, to have delta t very small because Newton's second law works best at a very small time in the future. Now comes the part where we will assign the right code to predict the motion of the object. This code simply means that while the time is less than 0.867 seconds, we assume that there is no force acting on our system. As a result, final velocity will equal to initial velocity. Then use the vector position equation to predict the new position of the moving object by adding the change in velocity by time to the initial positions, and this goes on and on. Let's now see visualizations of our computer model. In the code on Python, we can see that as we expected, the object is moving from positive x directions to negative x directions. A negative slope is formed. Using a spreadsheet, the experiment and the observation is plotted on the same graph. The dots represent the experiment and the lines represent the model. The results are slightly compatible. However, it makes sense that in our model, we over-predicted the momentum. In the experiment, we did have other forces acting on our system, but in the model, to prove the constant velocity of Newton's second law, we did neglect them all. The direction change, the object vector changes as well, but the velocity and the momentum will not be affected. And this can be proven in our graph right now. Only the signs of the slope changed. However, if we had some forces on our system by changing the F net, we can see that everything completely changed and the graph will not look like it used to look before. It will look like something like that.